this table indicates the chronology of the basement rocks of Sri Lanka. Okay, so you can see the all the complexes: Highland complex, Vanni complex, and Vijayan complex. But you don't see here the Kadugannava complex. But just keep in mind, Kadugannava complex has almost similar chronology as the Vanni complex. Okay, so but just the difference is it indicates some kind of deposition or crystallization natures, like but not sediment, the supracrustal rocks. Actually, do you know what these supracrustal rocks are? Supracrustal rocks means the rocks deposited in an unknown basin. That is the pelitic rocks, the sediments, metasediments. Okay, but the Kadugannava complex has very minor amount of metasediments, similar to Vanni complex ages. But there is the granitic intrusions in the Kadugannava complex, which is typically like 900 MA. Okay, so that's the difference there, but still it contains ages up to 1100 MA also, right? But it does not contain younger ages. So I mean, younger ages, they are 900. So 900 to 1100 MA age is therefore includes the majority of the rocks in the Kadugannava complex. The granulite grade metamorphism is same, like 540 to 665 age is there, right? For the all the complexes, including Highland complex and Vanni complex, you have this age, common age. But for the Vijayan complex, little bit younger ages are also there for as metamorphic ages. Okay, so that means like 450 plus ages are there, and the predominant metamorphism in the Vijayan complex is amphibolite grade. Okay, so that you have to keep in mind. But it doesn't mean that there are no granulite facies rocks, but there are some limited granulite facies rocks in the Vijayan complex also, like in the Potuville area, Charnokites. You have Charnokites in the Potuville region. Okay, and then there is some another process which has taken place in the Sri Lankan rocks that we call the in situ charnocitization, right? In situ charnocitization means sometimes we call arrested charnocitization. Okay, arrested charnokites. It's a amphibolite facies rock. The host rock is amphibolite facies, but from place to place you can find patches of granulite facies rocks within the host rock. So these patches are actually three-dimensional. That means if you see as a patch on the surface, actually it goes down, right? It's like a grid. There are, I mean, several patches interconnect. That's why we call it a grid. Okay, so there are some patches on the surface, but all these patches can be interconnected, right? These patches can be interconnected into three-dimensional channels, right? Into three-dimensional channels. These are related with some fluid activities, carbon dioxide bearing fluid activities, which has reduced the oxygen fugacity, the redox conditions, and has converted the rock into granulite facies, but only partially, right? It has changed only partially. That's why we call it arrested. That means the reaction has stopped in the middle, right, on the way. So this is a special phenomena. Typically, this aging for this process is 535 to 550. Okay, 535 to 550, particularly in the Vani complex, but in some places in the highland complex also you can find, right? Now we have found some very rare locations in the Vijayan complex as well, but predominantly this feature, this in situ characterization is available in the Vani complex, uh, and limited localities in highland complex. And now we can say very rare localities in the Vijayan complex. And another important activity is the post-tectonic granites. Post-tectonic granites means after the metamorphism, right? They intrude after the metamorphism. So normally, after the metamorphism, there are no tectonic processes because the metamorphism is the most vigorous time within the Earth's interior with several tectonic processes. Collision and compression, extension, everything is happening. Folding, faulting, everything is happening. So that is the tectonic period. But after this tectonic period, if any magmatic intrusion is there, we call such intrusions post-tectonic intrusions. Such intrusions are there, which are granites in Sri Lanka, like in the Thonigala granite, and Arangala granite in the southern Sri Lanka, like several Ambagaspiti granite. Several such locations are there. We consider them as post-tectonic, right? But it's debated. Some people argue that these are also metamorphosed. That means almost at the time of metamorphism, they may have at least intruded, right? But since they most of the age data is like towards the younger side, people prefer to consider them as post-tectonic granites, right? So therefore, I mean, there are no such like 600 ages, 600 MA ages, like all the ages are not there in these granites. That's why. Which is available only within the highland and Vani complex. This Thonigala is in the Vani complex, right? That is the biggest one available, K feldspar granite. And then there are some cooling ages reported, and of course these cooling ages are should give younger ages, but all ages are also there. That means some rocks may have finished their metamorphism by this time, right? By 611, because metamorphism is started like 665. It's as old as that age, but by 600 or 611, some metamorphism may have stopped. So then the rocks start to cool, right? So some new mineral growth can be found during this cooling process, like zircon, monazite, like new mineral growth can be found, and such minerals give cooling ages if you date them. From the Vani complex also you have some younger ages pertaining to cooling processes. Okay. So generally, we take the granulite phases metamorphism in Sri Lanka, like in average, as the peak time as the 550. Okay, although it started at 665 or some age older age, but we predominant rocks. If you analyze the zircon and see the population, you will see a big peak in zircon at 550, right? Big age peak you can see in 550. So therefore, we can consider that most of the metamorphism may have taken place at 550 MA, right? But it doesn't mean the range is invalid, right? The range is there, still there, but in average, you can consider 550 as the metamorphic age. But it's always better you give a range. So the most predominant age peak for this is 550, although you get the majority as 550, but still you can find a population, a broader population between 550 to 610. Okay. It's difficult to write with this trackpad. Okay, 550 to 610. Right, this age range we consider as the period of the broad period of the metamorphism in Sri Lanka. Okay, so this is how the chronology of Sri Lankan rocks is determined, mainly using zircon age, uranium lead isotopic dating. Right. So we can find some important points. Available uranium lead, zircon, monazite, and rutile. Some rutile ages are also there, right? Because these are accessory minerals, right? Zircon, monazite, rutile, they are accessory minerals, and they are having good. I mean, they are good hosts for uranium lead system. Therefore, we can easily analyze them with this system, and very robust. Especially zircon is a very robust mineral, and monazite and rutile also can give you good ages, and particularly cooling ages are very much received, I mean, obtained from monazite and rutile, because they most of those grains form during cooling processes. So anyway, these ages are compatible with a very late Proterozoic, very late Proterozoic high-grade metamorphism in Sri Lanka, like 550. Okay, right. And the orthonizers in the Vanni complex and Vijayan complex, orthonizers, that means meta-igneous rocks. They do not preserve ages older than 1100 MA. You saw that in the table. That is the maximum age. But now, very recent work has found some ages like 1.6 GA, that means 1100 MA. Ages have also been recorded, but not very commonly. This is, in general, you can say that it's 1100 MA. This is from Vanni complex, okay, not Vijayan, right? Vijayan anyway, 1100 is the maximum, right? From Vanni, there are some rare evidence for old ages than this. The Highland complex preserves old ages, especially even more than 2 billion years, especially from meta sedimentary rocks. We call detrital zircons. That means the zircons preserved in sedimentary rocks. They show very old cores, right? You saw some core rim zones in zircon, right? Some core regions. So if you have this type of core region, we call it a detrital zircon, right? So this core gives you an older age, whereas the rim gives you a younger age. It's mostly metamorphic age for the rim. Such zircons are many in the Highland complex. So therefore, we know Highland complex contains very old materials. And this chronology is very compatible, and we can correlate with the other terrains in the Gondwana. In the Gondwana supercontinent, we were part of it during the late Proterozoic times. India, Madagascar, and Tanzania, right? So these metamorphic evolution especially is equivalent with the southern India, Madagascar, and Tanzania. Not only that, some East Antarctica also, right? East Antarctica. So this is that indicates all these continents or the fragments were together at that time. Okay, right. And this is the some schematic map showing some age distribution with analyzed zircons and some of their locations. Okay, can you see? Uh, you see some ages. These are the references, uh, and this is the very extensive type of studies who did German team who did this isotopic analysis, and you can find orthogneises, pelites, meta sedimentary rocks, and meta basites, metamorphosed mafic rocks. Okay, orthogneises, includes everything, metamorphosed igneous rocks. Here, particularly the mafic rocks, the like gabbro, like meta gabbro, like rocks, and granites. Right? So this upper intercept, the thing means in zircon dating, this is something to do with the isotope geology lesson. Some ages are given. We use some diagram called Concordia diagram. Okay, Concordia diagram. There, when you analyze zircons, you can plot them, and sometimes their linear distribution is shown, right? So this linear distribution means this line crosscuts at two places of this Concordia line. We call this Concordia line. This is the evolution of the Earth line, Concordia line, right? Starting from the oldest ages to the present day, right? So the upper side intersection we call upper intersect, and the lower side intersect we call lower intersect. Okay, so actually we are supposed to get zircons uh, which must lie on this Concordia line. So if you have this type of zircon grain, when you plot your age data, the isotopic data, this is uranium lead isotope ratios. Okay, x and y axis shows. So this is a graduated curve, this Concordia, and if your sample plots here, and it corresponds to some age, say 2 billion years, because this curve has graduations like ages marked there, right? If it is 2 GA marked here, it's by default, it doesn't change, it is globally universal, it's no difference. Okay, so just you put your grain depending on your isotope ratio and get the age. It's very easy. Say it's 2 billion years, then we call it a concordant grain, because the grain exactly plotted on the curve, right? On or very near to the curve, we can directly get a age from that. That is, we call the crystallization age of that zircon. But if this zircon subjected to metamorphism at a later stage, uh, you might see this type of uh, uh, distribution. I mean, your zircon, it's not one zircon. We have to analyze several zircons, right? The population. So most of your zircons, if plotted like that outside the Concordia curve, and then this along those grains, you can make a regression line, a fair line representing all the grains, right? So in that case, we have an upper intersection and lower intersection. But in the previous case, you had only the grain plotted on the grain. But this type of plotting outside the Concordia means your zircon grain has been disturbed. Your isotopic systematics have been disturbed by a later process. For example, metamorphism. Metamorphism is a later process. After crystallization, the grain is subjected to metamorphism. So in that case, some lead loss is happening. So the grain, the isotopic ratio deviates from the expected value. So that's why you get outside plot. So such zircon population indicates two ages, lower intercept age and upper intercept age. So we get the age from this regression line. We call it a regression line. Okay, the previous grain was plotting on the curve, and therefore we call it concordant grain. But these grains are plotting outside the curve. They are not concordant. Therefore, we call it discordant grain. So The line we join the discordant grains we call discordia line. So this discordia line intersects at two places of the concordia curve, the lower intercept and upper intercept. The lower intercept shows the disturbance age. That means a later process which has made the isotopic systematics disturbed. Reset, we call it reset, resetting of the uranium lead system. You will learn these things in your isotope geology lectures in the next year. But the upper intercept indicates their crystallization age. For if the metamorphism did not affect these grains, all grains must lie somewhere here on the concordia itself, okay, at the upper place. But now they do not lie on the concordia. They are plotted like here in a discordant manner. But the intersections will give you their crystallization ages, old age, the two ages. Crystallization age is from the upper intercept, and the lower intercept gives the metamorphic age, the later process. Okay, so that's why here, for example, this granite, within bracket it says upper intercept. That means they have shown here this plotted ages shows some upper intercept ages, right? That's why they are given. Some grains might show you very young upper intercept ages, while some grains might show you higher higher values of ages, right? Old ages. Like for example, here maybe 2.5 GA for the upper intercept, and for the lower intercept maybe 550 MA, like that. Okay, such ages can be found, but this distribution, I mean, in this map you can't find it clearly, but here they have mentioned it is upper intercept. That's why I mentioned. But if you see the concordia diagram, then definitely you can distinguish them, right? So these ages for different rocks, peelites, quartzites, and many other types of rocks, and they have plotted them on the map, right? So for geochronology, people have used this age mapping. That's how these complexes are also recognized, the Vanni, Highland, and Vijayan. But for boundary determination, some other isotopic systematics have been employed that we call neodymium model ages. Okay, that is something else. I mean, there is a samarium neodymium system. I think you can remember we mentioned about that. That can give you some ages called model ages, right? This model age mean uh, the whatever the rock you are considering here, for example, and if this rock was originally formed as a product from the mantle, Earth's mantle, and maybe it was there in the mantle at the original times, but later on it has separated from the mantle due to some melting events later, mantle melting, because mantle can melt and produce a liquid melt that comes up to the shallow levels and make the continental crust. Okay, this is the continental crust name. So the rocks lying here in the crust are like this type of deposition, this type of crystallizations. So the timing of that particular rock which left the mantle, that means this timing of this leaving of this mantle residence time, right? That time is given by the model ages. Model ages. So uh, for many rocks, for these all complexes, the model ages have been determined and found that the Highland complex has the oldest model ages. That's why I mean there is some contrast between these ages, and that's how they have been able to draw this boundary line. Okay, just because of this model ages. It's called model age mapping. So the Highland complex shows older model ages like 2000, 3000, like that. But for the Vijayan and Vanni, there are younger model ages, less than 1000 or 1300 or 200 2000 or something like that, less than that anyway, less than the highland complex. So that contrast was used to make these boundaries, and therefore these boundaries are called isotopic boundaries. Okay, these boundaries are called isotopic boundaries, and this age mapping, isotopic age mapping, has been used for several terrains in the world, including Sri Lanka. But there are some concerns about these ones continuously discussing, because these samples, I mean, these boundaries uh, do not comply with the structural trend of the country, right? For example, in this region, the structural trends are like this. Okay, if you see the trends of the foliation and the other lineations and other directions, they are cross-cutting this boundary. So how it is consistent with this boundary? Because it should be along the line. In that case, like this, the boundary should be at least something like this, right? If it was drawn like that, then it might be okay. But the problem is the isotopic edges are not matching if you draw like that. This is totally an isotopic age mapping. Therefore, uh, there are some discussions that these might not be exact boundaries for the complexes. But anyway, for the time being, we are using them, and based on the lithologies and other petrological and geochemical contrast existing between these two complexes, still these boundaries could be considered as valid, at least for the time being. Okay. Right. So this is the geochronology, or the geological crustal unit classification, which uh, which was aided by the neodymium isotopic mapping. And also it is helped with this zircon data as well, because zircon data also shows older rocks are available within the highland side, whereas other younger ones are available in the two other sides. So therefore, still people are confident about the age boundaries, although there should be some revisions necessary for some parts of this boundary. Okay, if you consider the older age data, for example, the rubidium strontium, I mean, some decades ago, people did some studies on rubidium strontium as well. So these ages are also inconsistent with those other systematics as well, right? But not 100%, but it's okay, acceptable, right? But the grade of metamorphism uh, is different, granulite phases and amphibolite phases, but that has nothing to do with the age. But only thing is why such great difference came within the same period of metamorphism, right? Because we consider like the very broad range for 450 to 665 or something. If you consider the whole range of ages, all Highland, Vanni, Vijayan, the three complexes both can be put into this age frame. But still, some metamorphic grades are different. That means some other controls should have been there during this metamorphism. Okay, right. So, just to show you some analysis, some zircon analysis. Uh, some zircon analysis. These are the zircon grains, right? Individual zircon grains, and you can see some spots there, right? Actually, this is a kind of a crater, right? It's a hole. Why this happens? During the isotopic analysis for this age dating, right? This zircon uranium lead age dating, you have to take some tiny amount of material and dissolve it or evaporate it and put into the mass spectrometer, ICP-MS. For that, This micro type of pits are generated with an ion beam. Uh, it can be either laser spot or SIMS, the other instrument. I think I mentioned about these things in mass spectrometry part in the very beginning, right? See, secondary ion mass spectrometry or uh, laser ablation technique. Okay, laser ablation, LAICPMS. That means all these laser instrument is connected with an ICPMS. Okay, ICPMS is necessary for this age dating with the laser. But for SIMS or shrimp, there are two machines. SIMS mass spectrometry MS. Okay, SIMS or shrimp are both utilizing an ion beam, not laser beam or anything, ion beam. Uh, with those beams, you can make a hole, very tiny micro. This is like 20 micrometer, very tiny, very small, uh, uh, very small pit you can make and get the material and measure them for isotope systematics. That's how you get the ages. For example, core. This is a core age coming from a zircon because this is the core region of the zircon, and this is the rim region of the zircon. And this entire zircon is like maybe, yeah, you can see the scale bar here. 0.1 millimeter indicates this length. Okay, so think of the length of this zircon grain, how tiny it is, right? Maybe few hundred micrometers, maybe 150 or 200 micrometers or something like that. But even lesser that, even smaller than that. So if you have little bigger grains, then you can analyze several spots to be more confident, right? But we select these spots before analysis by using some other technique called cathodoluminescence. We call CL images, cathodoluminescence images, equipped with an SCM or electron probe. Okay, so even our SCM, which is available in our department, if we have a CL detector, if we have a CL, we call it a detector, and fix it to our SCM, we can see cathodoluminescence images. And these images will show you internal structures. So you can find out whether this is having a core like this or what kind of a zoning, something like that. Right? This is just optical image, nothing. No internal structures are shown. This is only the surface structures. Okay, this is optical image by microscope. You can observe with an SCM and get the CL images and then decide, okay, which point we are going to analyze, this or this or this, like that. Okay, so this shrimp machine is a very new type of technology has been employed. Of course, the machine has been invented some years ago, maybe more than 15 years ago, but now new versions of shrimp has arrived in several labs in the world. Right? First they produced in Australian National University, a product of them, shrimp instrument. But later, now it's actually it has been transferred. The ownership has been transferred to China, Beijing. Now the China produces shrimp. The new, very high technology shrimps are now being produced. So this is called sensitive high resolution ion microscope. It's actually a SIMS, secondary ion mass spectrometer, the same type, right? SIMS is another device, but this gives more high resolution. That means you can look into more and more details in very tiny areas. That's why we call it high resolution, right? That indicates even very small grains of zircons can be analyzed, which was unable before using laser or ordinary SIMs, right? Laser is a little bit difficult because laser needs a little bit bigger grains since their spot size is bigger, right? Their spot size is much bigger than SIMs. So therefore, if you have a very tiny grain, you may not be able to analyze by laser. You have to go to SIMS or shrimp, right? So anyway, the zircon morphology and is very important to for us to get the patterns because some morphology determines whether these grains are deposited in a basin and then transported long so that we can identify them as detrital grains, right? You see some rounded grains, right? And also you have some angular grains, which indicates the mode of transportation might not be uh, very long, like, okay, see, you have edges, angles surrounding. They are not transported because all these the cones are transported during some thousands of million years ago by erosion and other processes, right? Stream transportation. That's why they are got rounded. They just got rounded. So by these grains, these old ages, this is like 1 yen high, 1 yen Vijayan, but for highland, greater than 2 GA ages have been reported from these old cores of the cones. Okay, so this is one equipment this geochronology is facilitated with. So it's an important equipment. Sri Lankan rocks have been analyzed by this method as well. But you don't see many analysis by from shrimp because shrimp is a very expensive device, right? To analyze, you need to pay a lot of money because analytical charges are very high due to maintenance costs of these machines. Sims is also same, but laser is relatively cheaper. So when we see when zircon population is analyzed, you will see this type of the variation in isotopic ratios. Okay, so these are the ratios uh, uh, measured by these mass spectrometers. Okay, so after that, age should be calculated. For some programs are there to calculate ages, and then you can plot similar histogram, and maybe you will see some age peaks coming out from these the cones at different ages, and maybe uh, two types of peaks you might encounter. For histogram, normally we take the number of zircons n and the age here, right, against the age. So obviously the Sri Lankan zircons will show you definite population around 550 MA. Okay, around 550 MA, there will be a definite population, and you might get another population if it is from highland complex somewhere more than 2000 MA, right? If it is from Vani complex, you will get 1100 like H peak plus 550 H peak, because metamorphism is one event, the crystallization is another event. Okay, so this is how we characterize the crystallization ages and metamorphic ages related to these grains. Some analysis, some studies have done for the Sri Lankan rocks. This is the first study on river sediments, okay, from river sand. So actually, this results this research is an extension from an undergraduate project, right? of our department, and we found extensive age peaks. You see here, this is what I mentioned, the age peaks, right? Different age peaks. This is around 550 age peak. This is also 550. So you can see at 550 there are so many HP. I mean, all the sample, all the rivers of Sri Lanka. These are the rivers. The locations are shown in this in the places where the samples were taken. Right, Kalani, Kalu, Walave, Mahaveli, Mahaoya, Madruoya, like all these, and yeah, Nilwala, all these rivers. Some samples were taken and analyzed. Some grains, I think, more than at least, yeah, you can see this n number. This number indicates the number of grains. At least 50 grains from each river. Here, 25. Uh, Here, 112 grains, right? Likewise, the higher the number would be better. But the thing is, the analysis is very expensive. So we have some limitations. So anyway, you can see some secondary peaks also, right? You can see some secondary peaks. These indicate some process has uh, been there in the Sri Lankan crust, probably during the crystallization time of these zircons, may be related with the crustal derivation, crustal production, right? For example, I mentioned before, remember the mantle melts and produce crustal, the continental crust, right? So these ages, there may be several stages. Okay, there are several stages of peaks you can see. That means multiple times of melting has been observed uh, by this population. All these are cones, but shows uh, age peak at 550 also. That means all these cones have, all these originally formed cones have subjected to metamorphism at that time. So metamorphism and the multiple crystallization time. So this indicates kind of an episodic crustal growth, right? So you can refer this paper. Uh, this was published in Journal of Asian Earth Science. We discuss there about the episodic crustal growth as observed from the Sri Lankan rocks, right? So it's a contribution to the global crustal evolution. Right? So these are some examples, and if you see the most of the rivers in the world, like large rivers, Amazon, Mississippi, or Yangtze, Yellow River, Indian rivers, etc. Right? They will also have these minor peaks like this, consistent with the crustal growth. So that means we all, the continents, all these continents, most of the global continents were suffering several crustal growth events during the past. So these can be compared in this type of a study. Okay, so this is in this paper you can find in the reference list something, another paper called Reno et al. Reno, RINO, Reno et al. 2008, that shows you about the global river system. There, how they have sampled, and how that contributes to crustal growth. But anyway, remember, not only from rocks of Sri Lanka, the river sediments uh, also contributed for age dating. And also now there is another paper in 2020, yeah, this year, 23, in the pre-chem, no, still the same journal, Journal of Asian Earth Science. Uh, There you can find the beach sediments, Sri Lankan beach sediments, the sediments from the beach sand, maybe, yeah, in the southern region mainly, has contributed to how they have contributed to crustal growth. Okay, that paper you can find as Atira et al. 2023. we also co-authored that one, and Dharma Prisa also a co-author there, right? Adira et al. She's an Indian student. Okay, so we have extensive age dating for rocks uh, in the recent times, because these ages are very old actually. That is like 1990s, right? A long time ago. But we wanted to do further analysis, and during Dharma Prisa's PhD, we did uh, laser ICP-MS analysis, uranium-lead ages of detrital zircons we mainly selected, right? You can see the detrital zircons. You have core, you have rim, and these are the images taken from cathodoluminescence. I mentioned it before, right? Remember? CL images, right? These are just optical images. These are just optical images because at that time, this is an old paper, 1987, I think, this paper, but still Sri Lankan paper by Kronetel, German group. But that time, I think they didn't have this CL imaging facility. That's why they don't have those images. So now we have these CL images, and you can see the internal structures. This growth structures very, very beautifully grown zircons. One stage here, and another stage here, and the last stage here. So you see, the older ages are given by the central part, core part, the oldest area, and then the second region you get little younger age, 833. That means one crystallization process has taken place, original crystallization process, and then later some kind of another growth on top of the grain. This can be happen during the magma evolution, because the mantle melts material, and the materials are coming up to make the continental crust. But during the growth of the crystallization time here, the time of crystallization refers this place. But later on, during this magma ascent to the crustal levels, it takes some millions of years, right? Some growth can take place. Okay, so these are the later growths, and finally, the metamorphic age, metamorphic time, the giving this type of a clear rim. See, you can see very clear rim which shows a dark, light color, whitish appearance compared to the previous zones. Those are different. Compositions are different, right? So it's giving 599 here in this grain, like that, right? So here you have a very old grain, 1700 something, and here also you have a very beautiful detrital grain with very nice zoning. We call this oscillatory zoning. Okay, in igneous petrology, you can learn about these things. Oscillatory zoning. This means the crystallization and growth of the zircon, right? And at the interior, this is not actually the rim. This is still the mantle part. We call core here, core, rim, core, mantle, and then rim. Okay, the rim is the exterior part. Uh, Between the core and rim, you have the mantle. So this is mantle area. So rim should be this area, right? But for this grain, this area is too tiny, right? It's very small to analyze with the iron probe, with the same source stream. That's why it is not, you don't see any spot, yellow spot there, right? This yellow spot means the place where you analyzed, right? But this CL imaging, cathodoluminescent imaging, is taken before the analysis, right? Before the analysis. Therefore, you don't see that spot, okay? You don't see that physical spot which you saw here, right? These grains are after analysis, they have shown, they have taken images, right? But CL imaging has to be done before the analysis to identify which areas of the grain we should select. Okay, therefore you don't see these spots. So anyway, this is the Concordia curve. So you can see the Concordia curve here, and these numbers represent the age. I mean graduations of these Concordia. You can find from 0 here to 4.5 billion years here. but this will be very extending, like this. Okay, now this is just a segment, like this small segment is shown here. Uh, some of the grains are very concordant. See, some grains are very concordant, whereas some are plotting outside the concordia curve. But they are still very close to the concordia, therefore no problem. You can take them. But if you get some grains like here, very outside, and you can see here one here, this is discordant grain. And if you had a population here, you could have make a line like this. This is what you call the discordia line, and you get an upper intercept and you get a lower intercept, so that you can find different ages if you had. But normally, if you had such an intercept, such a discordia, most probably you will have something like this, because the lower intercept is close to the 550 or something, right? Metamorphic age. It should be close to metamorphic age. Okay, so this is one example of a very recent time. So this indicates some ages in this range by from this study, right? And it is correlated with Sri Lanka and India, the Gondwanan linkage. And another one, this is 2014. This one 2016, I think. This is 2014. Uh, Again, some zircons, but you can see these grains are very dark, right, compared to the previous ones. It depends. We can't say why this is dark and why this is bright, right? It also depends on the CL imaging also, but still you can see the internal structures, right? You can see the internal structures, and you can see the ages also obtained uh, with this analysis. The second number, this tiny small number, indicates the uncertainty or the error, plus or minus value, right? Always we get a plus or minus value also for the age. It's not an exact age, but you have some variation, very small variation should be like 4 billion years, 5 billion years, that will be okay. So this indicates 540 plus 4 or minus. That means it can be 544 or it can be 536 also, like that, right? So these are also CL images, cathodoluminescence images. And here again, some important findings with respect to uranium lead, and also lutetium hafnium isotopic systematics also. Like neodymium modulages I mentioned before, it's possible to get hafnium modulages also, right? Uh, for neodymium like hafnium, and modulages can be obtained and compared. And Sri Lankan rocks are consistent with the neodymium modulages when you compare it with hafnium modulages also. Okay, right. And yeah, I think this is what I mentioned before. This one, the publication for this one, Asian Earth Science, and you see the detrital grains. So this is Mahaveli, River Mahaveli, and this is Kalani grains, and you see very beautiful grains, detrital grains, very nice. This is like 3,391 million years old. But the other part, the rim part or the mantle part, gives you 549. That is the metamorphic time. So on top of this detrital grain, new growth has taken place during this metamorphism. And you see very nice grains with this oscillatory zoning. And from Kalani also very old ages are there, 2.3 billion years, and the metamorphic age coming from the rim area. And you can see one grain has given 900, something like 900, right? This is Kalani. So it's passing parts of the Vanni and Kadugannav complexes also. So probably this zircon grain has come from to the river from Kadugannav complex. So you get 900 some ages. You remember I mentioned that crystallization age for the Kadugannav complex is around 900 MA. right? So likewise, we can resolve these populations if you make a plot like this, right? If you make a plot like that, it's possible. So anyway, this chronology of evolution is compatible, as I said before. The southern India, Madagascar, Tanzania, and East Antarctica. Uh, we have the supercontinental growth evidence are found from our rocks as well, and we could correlate them with the other Gondwana terrains. That indicates all these terrains were part of the East African orogene. That means the Mozambique Belt Formation time. So this is the Pan-African Mozambique Belt means the Gondwana was formed by two huge continental blocks, right? East Gondwana and West Gondwana. These two were collided. Okay, so these two were collided and formed a mountain belt. Right, this collision, continental collision. These are supercontinents, very large. You know how big is a continent, right? Asia, America, Africa. Just those are continents. But supercontinent means more than 80% of land mass is collected into one continent. Right. So think of how large that is. So they create huge orogenic belts, huge mountain belts. So Sri Lanka was also very close to this orogenic belt somewhere here, and India was also here, right? And Antarctica was here, and Madagascar was here, sorry, Tanzania was here, Madagascar was here, like that. So every terrain was together during this Gondwana, African, this Pan-African orogenic time. Okay, so this collision caused large continental fragments to amalgamate. That means to come to each other, close to each other, and collide to form the final Gondwana supercontinent during the Pan-African time. Actually, the Pan-African time means around 550 million years age. So this is just a name given for that age because it is first discovered from the African continent, African countries, this age determination. So our metamorphic evolution is consistent with this Pan-African metamorphic belt formation. This study particularly helped to correlate the southern India, particularly because southern India shows very similar rock types, similar metamorphic grades, similar metamorphic ages with our terrains, especially with highland complex, right? So to correlate these two terrains that we were together at that time, these ages were very helpful, right? In this paper that describes. Okay, right. So this is the last part that I had to cover under the geology of Sri Lanka. Do you have any questions regarding this geochronology part? I didn't want to go through the theoretical aspects because it's too much for you if I do that now. I mean, age equations. There are equations to derive for age determination. But I didn't do that. It will be done at the fourth year. Those who will join the special batch will learn about those things at that time. Okay, so this is the main concept of the geochronology of Sri Lanka, and you need to read some of these papers that I mentioned. And I will put them in the Google Classroom. So you can't, I mean, you can't understand all the content, but at least some parts you should understand about the geochronology. Like for example, if you take a map like this, and you should be able to explain what has happened there, what is done there, like that, right? And what kind of ages were there, what is lacking in Vani complex, what don't you have, and what are the rock types that gave ages uh, of 1100 MA in Vani complex, and in contrast to the Highland complex rocks, what kind of zircon grains available, and what kind of morphologies are there, what is the meaning of core rim zoning, like that, right? So these basic understanding is very, very important. So you have to go through some of the sections. Okay, so do you have any questions? If you have any question, you can ask now. Today I'm finishing my part of the lectures. So you can remember I started with the complexes, right? The classification of the Sri Lankan metamorphic basement, and then we touched with some supercontinents, Gondwana formation, and those things, and then uh, we 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 came up to this geochronology part. Okay, so please sign the attendance, and you will get some assignments uh, or the materials. Uh, I can't remember. Oh yeah, yeah. I haven't given you the papers, right? These geochronology papers, relevant ones. So I will check them in the Google Classroom and upload. And in between, I might ask you to do some assignment as well. Okay, right. So I am now finishing the session today.